In this video, we'll close out our round by calculating the confidence interval for proportions. This is going to feel very similar to what we've done before. In fact, the confidence interval for proportions is going to use the z-scores, not the t-distribution that we were using in the last one when the standard deviation was unknown. So we'll just jump right into it. Again, the interpretations and what we're going to end up doing is very similar to what we did before. The only addition is because we're using proportions, we'll be doing some different calculations. So recall that P is the population proportion. In this case, we'll use P hat, so the P with a little hat over it, to represent the sample proportion. And this is just going to look like the number of successes divided by the total number of trials. This is how we calculated our empirical probability before. And then Q hat's just going to be 1 minus P hat. You could use this formula if you prefer, but I tend to like the 1 minus P hat notation. Makes life a little bit easier. And again, X is the number of successes, or the number of samples that units that possess the characteristic of interest, and N is our sample size. So in this example, in a recent survey of 150 households, 54 had air conditioning. We're going to want to find the proportions that had air conditioning and the proportions that don't. So this is going to be really straightforward. We just look at the total number who have air conditioning, 54, divided by the total number of total households, and that gives us about 36% of households have air conditioning. For the opposite, we'll just use 1 minus this. So 1 minus 0.36 gives us 0.64, so about 64% of households don't. If you want to use the other equation, you sure can. Just sub in X and N. So we get 150 minus 54, or 96 individuals who don't have central AC. So 96 out of 150, that gives us that 64% of households who don't have central AC. Now in this case, we're going to still be using the z sub alpha over 2, but now we're going to be using the square root of p hat q hat divided by n. So this is different. Normally we have sigma divided by the square root of n, or s divided by the square root of n. Now we're going to have the square root of p hat times q hat divided by the square root of n. Our full formula is going to be p hat plus or minus z sub alpha over 2 times the square root of p hat times q hat divided by n. Now, there is a requirement when we're doing this, and that is that the sample size times the proportion is greater than 5. So this is both the sample size times the proportion of successes and the sample size times the proportion of failures. We want them to be greater than or equal to 5. This is for technical reasons with the binomial distribution. Frankly, if they get closer, the distribution becomes too skewed for the normal approximation to be appropriate. And the normal approximation is the basis for the use of this formula. Note that we're using the normal distribution here in our critical value. For some other assumptions, note that we're still assuming that this is a random sample. And when we're using the proportions, now we're assuming that the conditions of a binomial experiment apply. So all of the assumptions that we made for a binomial experiment, we assume are applicable here. All right, for example, we have a survey. We're interviewing 1,404 respondents, and we find that 323 students paid their education via student loans. And we're asking you to calculate a 90% confidence interval. Feel free to go on and try this on your own, actually. So go on and pause. Give this one a shot using the previous formula. See how you do. Coming back, we can look. So we want a 90% confidence interval. That means we have a 10% error rate. So alpha is going to be 0.1. Our z-score for an alpha of 0.1, recall how we went in the z. We did that 0.1 divided by 2. That gives us 0.05. And we're looking for the z-score with an area of 0.05 below it. That's going to be positive or negative 1.645. Our point estimates for p hat are just going to be the total number of successes, 323 students paying with student loans, divided by the total number of observations, 1,404. And then q hat, again, I would do 1 minus p, so 1 minus this 323 divided by 1,404. Now we just plug the values in. So we have our values for p hat, our values for q hat, plugging those in to our equation. and our values for z and p hat at the beginning. Solving, we have the confidence interval between 0.2116 and 0.2485. So we're 95% confident that the proportion of students paying for college loans is somewhere between, with student loans, is somewhere between 21% and 25%. And that the true proportion lies within these bounds. Again, this is the exact same interpretation that we had earlier, except now we're doing it with proportions. Go on and give this one a shot on your own. Now think about this. If we have 15.9% of individuals purchasing the books, note that you've already been given one of your values. So take a second, give this one a shot on your own, see if you can figure that out. Coming back, for our 95% confidence interval, we find z sub alpha over 2 is 1.96. Our point estimate of p hat is 0.159, and this is what we were given in this percentage. So you're already given the proportion of individuals who have success or who have purchased religious books at a Christian bookstore. And then we've got our q hat of 0.841. And that's just 1 minus p hat. So don't miss the forest for the trees here. Don't freak out because you don't have the number of individuals who have a success, because they've already given you the percentage, and that's what you were going to use that number to find anyway. Plugging these values into our confidence interval, we find that the 95% confidence interval of the population proportion of people who buy religious books at bookstores is somewhere between about 14% and about 18%, give or take. So this is a reasonable range of percentages that we would expect to find people who buy religious books at a Christian bookstore. Now, just as we calculated sample size before, we can also do sample size here. So our margin of error is a little bit different here. We can actually just solve this equation for little n, and that's exactly what we do in order to find the sample size. So all we need is the population proportion. Remember that once we have p, we can solve for q. We need z, and we need our margin of error. And that gives us our estimate for the sample size. So in this case, we have a 95% confidence. We want the proportion of people who own a home computer. A previous study says 40% have a computer at home, and we want to be within 2% of correct. So our margin of error is going to be 2%. Our proportion that we're going into this with is 40%, and we can allow a 5% chance of error. That is, we want to be 5%, 95% confident. The 5% chance of error implies that our z-score is 1.96, and once we're here, we simply plug all of these values into our formula. Our recommended sample size, we've got 2,304 participants, but remember we round up 0.96, so this is going to be 2,305 individuals are necessary to estimate this proportion with 95% confidence to be within 2% of its actual value. Incidentally, this calculation is a bit simplistic, but calculations similar to this are how we run population polling when they're doing things like political polls and want to be accurate to within 2%. How many individuals do they need to survey to be accurate to within 2%? All right, in closing, I want to talk about one of the most useful ways that we can apply confidence intervals in real-world situations. So I'm just going to scroll back to a different example here. So let's just use one of these examples. This is the, representing the number of assets of 30 credit unions. And our prediction was that for the 30 credit unions, their mean assets are somewhere between $6.5 million and $15.5 million dollars. So what if somebody proposed that in these credit unions, the mean number of assets for these credit unions was $20 million? That somebody said this and you wanted to check it out. So you got this data, you calculated the confidence interval, and you found that a reasonable range was between $6.5 million and $15.5 million. Well, we're 90% confident that this true mean value is in this range. So if there was a proposal that the true mean value were $20 million, we really wouldn't tend to buy that proposal. We would say that, hey, our data don't really support that decision. Let's go to a different example here. So we're looking at the mean hours of sleep per night. And let's say that somebody proposed that from this sample that the people were randomly selected from, let's say these were college students, 10 randomly selected college students. Let's say that somebody proposed that college students sleep on average about 10 hours per night. For whatever reason, they just believed that college students sleep 10 hours per night. And so we went and we calculated data. We gathered data on these 10 people. We calculated the mean, the standard deviation, and then we ultimately calculated a confidence interval. And our confidence interval suggests that college students sleep between 6.5 and 7.5 hours per night, certainly not even close to the 10 hours per night that somebody proposed. In this case, because our confidence interval indicates, again, 95% confident that we're between 6.5 and 7.5 hours per night for these students, we would tend to not believe an individual who proposed that actually the real number is 10 hours. Our data just don't seem to support that. We're 95% confidence between 6.5 and 7.5 hours. It doesn't mean it's impossible that the real value is 10 hours. It just means it's pretty unlikely. It's smaller than a 5% chance. Now let's contrast that. Let's say we're looking at the number of students who pay their education by student loans. This is an example we did in this. We said between 21 and 24 or 25%. Now, if somebody proposed that 22% of the students paid for their education using student loans, that would actually be a number that this data supports. Now, we don't know if it's exactly 22%, but what we could say is that 22% is in the reasonable range. So the idea that I'm proposing in these examples is that we can use the confidence interval to assess certain individuals' claims on what should or is. So if somebody said that the proportion of students is 22% who pay for their student loans or pay for their education with student loans, we would say that our data don't disagree with that. That very well could be the right answer. Whereas in the previous case, if we had individuals who were saying that college students get 10 hours of sleep, or if we had a claim that on average these businesses make $20 million, we might say that the data don't support that because those values of 20 million and 10 hours of sleep are outside of our confidence interval, we really don't believe that those are true. We tend to believe that it's only numbers within our confidence interval that are likely to be true. Again, we could be wrong, but there's a good chance that we're right, and it depends on how we constructed the confidence interval. So in this case, there's a 90% chance that we're right. We could be wrong, but there's a 90% chance that if we ran this 1,000,000 times, that the true value would be within these. If we ran a whole bunch of these different simulations, or we could make this a 95% or a 99% confidence interval to determine those probabilities. When we talk about this, I want you to think through the idea that confidence intervals provide a reasonable range. And using this reasonable range, we can assess the strength and validity of claims about a specific number. So we could assess the validity of a claim about 50% of college students pay for their education with student loans. Our data just wouldn't seem to support that claim. Versus a claim of 22% of college students pay for their education with student loans. Our data do support that claim. We don't have any evidence against that. So we can use these confidence intervals to support or dispute claims about the variables that we're studying. Note, when you're supporting and disputing claims, though, it is very heavily dependent on the sample. So where you took this sample and making sure that the sample that you're discussing is the same sample that a claim is made on is very important. And this is the end. So again, you have your journals that are due, not a week from today, of course, but at some point. So please make sure you fill those out. That ends chapter 7. In the next chapter, we'll get to talk about hypothesis testing. And this is something that I've alluded to with this ending discussion on confidence intervals. I'll say that as we go into hypothesis testing, I urge you to consider this ending discussion on confidence intervals because hypothesis testing has fallen a bit out of favor. In fact, the American Statistical Association has highly recommended confidence intervals to replace hypothesis testing in the ways that I've discussed at the end of our video today. So we'll still talk about hypothesis testing. It's very important to understand the history of statistics, and it's also very often done still. But just consider as we go through this, maybe come back and listen to the end of this lecture, which may make a little more sense after we talk about hypothesis testing. So that you can get a complete picture of what the hypothesis testing framework looks like, especially in light of confidence intervals.